Our final project is an FPGA implementation of the GenASM framework developed with Vivado HLS. And before I explain what the GenASM framework is, I need to explain the problem that it seeks to address, which is the read mapping step of genome sequence analysis. So once fragments of DNA are sequenced and returned as DNA reads, which are strings of nucleotides, they need to be mapped back to the reference genome, and they could be mapped to one or more possible locations. However, mapping them back is a non-trivial procedure because these reads cannot always be mapped back exactly due to expected genetic variations in the sequences or just due to errors from the sequencing process. And so one large computational bottleneck in this read mapping procedure is the requirement for approximate string matching, which is what GenASM tries to accelerate. We decided to implement this framework not only because it's a state-of-the-art framework and has multiple applications, but because it's specifically a good fit for an FPGA implementation. It is the first framework based on the Bitap algorithm, which only uses simple bitwise operations and only needs to operate on simple integer bit vectors, and also has a lot of opportunity for parallelization. So the GenASM framework is split into two distinct portions. One, GenASM-DC, which is a edit distance calculation accelerator, which is specifically a Bitap accelerator. And then two, GenASM-TB, which performs traceback on the returned bit vector outputs from GenASM-DC to check the alignment. So our approach for this project was to start with the baseline software implementation from the GenASM publication, which is written in C, then to refactor the code into a hardware and software split that we thought made sense for implementing a hardware design, and then to optimize our baseline hardware design by changing the code and adding HLS optimizations, and finally deploying it on the FPGA and comparing the performance.
GenASM-DC, the first part of the GenASM framework, uses the Bitap algorithm to do approximate string matching, which is faster than dynamic programming algorithms because it only uses simple bitwise operations. It takes three inputs: a text string, which is the reference string, a pattern string, which is to be matched against the reference string, and then K, which is a max allowable edit distance. It then outputs the traceback matrix bit vectors for all text positions and edit distances, which is going to be used by GenASM-TB later. So this is a simple example of how the Bitap algorithm works. The DSIM vectors are calculated through simple bitwise operations and then are stored in the traceback matrices for further use. So we were able to further parallelize the Bitap algorithm by recognizing that there were uniform recurrence equations indicated by the code here, which had constant distance dependencies. This then enabled us, since we were able to acknowledge this, implement a systolic array. And we were able to do that through mapping the inner loop spatially through unrolling, and then mapping the outer loop temporally through pipelining. And then we were able to get rid of the inter-iteration dependencies by storing the previous values locally. So the linear systolic array in hardware was achieved through pipelining and unrolling, and the systolic array has a depth of 64 cores. We were also able to achieve an II of 1 through partitioning and reshaping the traceback BRAMs for higher bit width parallel access. And these tracebacks matrices are stored in the FPGA-DRAM, unlike the ASIC SRAM in the paper. So GenASM-TB, or the traceback algorithm, utilizes these traceback matrix bit vectors that are taken from GenASM-DC to form an optimal alignment. So at each position, The algorithm considers match, insertion, substitution, and deletion, which is indicated by a 0 in the status bit vector, and then forms a cigar string at this optimal alignment, which indicates where the substitution, matches, insertions, and deletions are. So this figure indicates or shows the traceback algorithm in hardware, and shows the traceback BRAMs that store the traceback matrices and are shared by the GenASM-DC and GenASM-TB framework. So here is the traceback algorithm pseudocode. So the variable length loop that runs the traceback algorithm was pipelined to optimize it and achieved an II of 4. And then the cigar string is stored as a character array and returned.
For deploying our GenASM framework on hardware, we use the ZCO104 board, and we use the Xilinx STSoC framework to develop the host, ELF, and the bitstream, as it's very easy to accelerate software functions and hardware using STSoC. In terms of our system design, we have a contiguous region of memory that is shared between the ARM CPU and FPGA logic, and they use this shared memory region to exchange the input and output arguments and strings. An important part of our project was optimizing the FPGA and DRAM interface. We utilized the 128-bit bus width between the FPGA and DRAM for maximum efficiency. And we had pipelined burst mode accesses across high performance AXI master interfaces. We also packed many input and output arguments into the wide 128-bit words for maximum efficiency. Now, moving on to the results, our optimized GenASM framework was able to achieve around 7x speedup over the software baseline, which runs on the ARM CPU. And our optimized hardware was also gave us an improvement of over 17x relative to the unoptimized hardware baseline. Here we show the execution time breakdown of the baseline on optimized hardware. It's clear that we were able to reduce the computation by a lot, by around 45x, but still in the optimized design, the communication is a big bottleneck. Moreover, in terms of the resource usage, the VRAM was the most significant since we have very large traceback matrices. The other types of resources are fairly small. So despite our decent performance improvement, we also identify areas for future improvement. In particular, we can use a FPGA device with higher bandwidth memory instead of the DRAM for more improvement. We can also instantiate more GenASM engines for higher parallelism. Then we can also have a more complex hardware design to avoid constant switching between GenASM software and hardware. So in conclusion, we were able to successfully accelerate the GenASM framework by around 7x. And in particular, we were able to accelerate the computation by 45x. And we identified that communication is a big bottleneck in our design with areas for further future improvement. Now we'll move on to the demo. Hello, it's Umar here with the demo. I'm logged into my ZCU104 board over SSH, and here we have the host application and the two datasets, short and long reads. I'm going to launch the application in short read modes first. We have 500 alignment tests. Let's look at the last one. This alignment is of length 64, the maximum supported by the hardware. We have a maximum edit distance of 64. And when we run this alignment, both in GenASM software and hardware modes, we obtain the exact same alignment. And we get a speed of over 6x, which would be higher if we remove these printf statements. I'm going to launch the alignment in the long read mode. In this case, the dataset contains of alignments over 64 characters. For example, if you look at this one, it's 110 characters. and it has to launch the hardware and software multiple times because they only support a maximum alignment of 64 characters. Even in this case, we obtain the exact same alignments. So that's all for a demo. Thank you.